All right, good afternoon, everyone. Hope you all had a good weekend. I graded the exams, so I thought we'd start today by just going over the results of the exam. The average score on this exam was a 72.2. That's this number here. I don't know if you can see this. I know it's hard to see all these little numbers, but the average score was a 72. Compared to the first exam, the average score was a 73.7 on the first exam. And the standard deviation, which is the number that represents how far apart the scores were, like the spread of the scores, was a 20, which was consistent with what happened on the first exam. So what that's telling me is that, you know, the average is about the same and the standard deviation is about the same. So not a whole lot changed in terms of exam 1 to exam 2. But there were some other pretty dramatic changes. This chart, let's see on the right here. What this shows is every student who took the exam that I graded. The orange represents the grades for the students on exam 2, and it goes from highest to lowest. So the highest grade was a 112, and then the lowest grade was a 41. And the blue chart shows what that student got on the first exam. So like, for example, the student who got the highest score on the second exam got a 95 on the first exam. This student got a 82 on the second exam and a 93 on the first exam. So if you look at this chart, I've already done the data for us. 12 students' grades went up from exam 1. So from exam 1 to 2, we had 12 students who did better. We had 10 students who did worse. Now, of the 12 students that did better, their grades went up on an average of 14 points. So for the 12 students who improved their scores, it went up dramatically by about 14 points. For the students who went down, the average was 19 points. So it's weird. It's kind of a mixed bag here. It's hard to interpret what's going on here. We had fewer A's on the test. We only had 5 A's. We had 1 more B, we had 3 B's, we had 2 C's, and then 4 D's, same amount of D's on exam 1 and 2, but we had 3 more not passing on exam 2, all right? So I guess the big question is, you know, where do we go from here? Like, you know, I'm sure some of you are happy, some of you are concerned about your grades. So what I would like to see, for those of you who are concerned about your grade, what I'd like to see is we have 2 more exams. I'd like to see improvement. Okay, if you can show on the next exam that your grade goes up, and then on the final, your grade stays high. If you can somehow demonstrate that maybe one of these 2 exam grades was kind of an anomaly, where you just had a bad day, or you know, maybe you hadn't really figured out how to study yet or something. If we can show that one of those tests really doesn't fit with everything else you've done, then I will consider replacing your lowest exam score with your final exam score. But I'm not going to say that as a guarantee promise. You have to show improvement. Okay, so like you can't have another not passing exam. Okay, you have to be showing an upward trend. Does that make sense? All right, any questions about this?
Could I meet with you during one of your office times to kind of go over what may have gone wrong on my test?
Absolutely. Yep. I've already met with a few students who came into my office hours, and we've gone through their test a little bit. Yeah, feel free to do that. And if you can't make my office hours, you just have to make an appointment with me. So you can do that. You can send me an email, say, hey, you know, can you meet me on this day, this time, whatever, and I'll let you know if I can.
Thank you.
Mm-hmm. So what I'm going to do, because, you know, this test was really about the foundation of what you need for calculus. I know for some of you, you know, maybe you're a biology major, Cal 1 is all you need, and you're just going to move on and no more math for you. But for a lot of you, you're going to need to take Cal 2 and move down the road. And so this is fundamental stuff in terms of, you need to know power rule, you need to know product rule, quotient rule, chain rule. You need to know it, and you need to know it very, very well. And so I'm going to provide you some more like worksheets. I don't have anything ready for you right now, but I'm going to put together a worksheet of taking derivatives to practice more. so that you get to that point where you feel really good about it. Because in Cal 2, what the challenge in Cal 2 is that what we do in Cal 2 is the reverse operation of differentiation. So if you think of differentiation, what we're doing right now is being a process that takes a function and turns it into its derivative. We can already see that that's somewhat complicated, you know, when you have to incorporate all these rules. But Cal 2 is about going backwards. And it's almost impossible to go backwards if you don't know how to go the forward direction. So your success in Cal 2 is dependent on your comfort level with Cal 1. All right. So you want to become very, very comfortable with this process of differentiation. So I'm going to continue to kind of give you some drills to practice to get yourself, you know, to that level where you feel good. And, you know, you've got Google, you've got so much stuff online now. You can just like go to Google and type in derivative practice worksheet and just download something. And, you know, there's so many resources out there for you, but I'll provide you some myself. So that way you have something that you can look at, okay? And it'll be just for your own benefit. It's not, I don't want to make it like a thing where I'm like, oh, if you do it, I'll give you a bonus. I mean, the bonus is that you'll do well in Cal 2. That's the bonus, you know, if you can get these worksheets done. Okay. So any other questions, comments, or I have to say one more thing. I gave you a review, right? And I told you in the beginning, I really wanted to try and wean you away from reviews. So you have to kind of ask yourself, how would you have done on that test had I not given you that review? Like, could you have done that without me giving you kind of a template of what to do or what to be ready for, you know? So even if you feel good, even if you got a really good score on that test, like, do you feel like you could have done that without that review? You know, because that's where you want to be. You want to be at a place where you could do well without a review. Okay. I think I'm done. I think we can start today's material. We're going to start chapter 3. All right. Chapter 3 is called Inverse Functions. And the first 2 sections out of this chapter are a review from college algebra. So I don't intend on spending much time here. There's a few things that you need to be aware of. And there's a bunch of things that you should have learned already that I'm going to remind you of. So I would look at 3.1 and 3.2 as something where maybe you need to go back and take a look at this stuff if it doesn't seem that fresh to you. Because I know, you know, you've taken pre-cal, right? You have college algebra, pre-cal, and now Cal 1. So it's been at least one semester, one full semester that you haven't seen this stuff. So, you know, just keep that in mind. Okay, so we're going to quickly go through this. All right, this is all college algebra stuff. So I want to remind you of exponential functions. So in college algebra, you learn about these functions. They're very special functions. They're functions that look like this. F of x equals a to the x. So it's basically a number raised to the variable x. Examples of this would be something like 3 to the x, or maybe you have, I don't know, 1/2 raised to the x. But this number that's here is called the base of the exponential function. And when we graph these, they have a very, very special look to them. So does this look like, you remember exponential functions from college algebra, that they look like this? Yeah. Remember that kind of shape? They're very different than any other function that you study in college algebra up to that point. You know, up to that point, you're studying lines and parabolas and then polynomials and rational functions, and then you get to exponential functions. And they have this real strange property. Well, it's not strange, it's the property of the function that, you know, as you, let me widen this out a little bit. As you go to the right, the graph takes off. It starts going really, really fast growth. But as you go to the left, the graph gets closer and closer to 0, like an asymptote, like a horizontal asymptote. That's what all exponential functions look like. Okay, so I put something here for you to kind of think through. If we look at this graph of this function, what we see is that as x goes to infinity, which means as we go to the right, as our x values go to the right, the function's values start going up, right? And so as x goes to infinity, the function goes to infinity. Does that make sense from the picture? Yes, yes.
Yeah.
Okay, and then the other way, if x goes this way, if our x's go to the left, in other words, if x goes to negative infinity, our function starts to dive down and get closer and closer to 0. Now, it never actually gets there, but it gets closer to 0. So these are two limits everyone here needs to be comfortable with. Now, there's something that I didn't state that I should have, and I was wondering if anyone would know this from college algebra, is that this is the shape of a graph. If the number here is bigger than 1, this is what it looks like. Okay, so in other words, if a is greater than 1, I say it right here. If a is greater than 1, then we have this sort of shape. It doesn't always have to look like this, though. If a is less than 1, like a fraction, like 1/2, it actually is the same picture, but reflected over the y-axis. So again, this is the graph. Oops. This is the graph if a is greater than 1. And then this is the graph if the a is less than 1, but also greater than 0. So the red one back in college algebra is what we call exponential growth. And the blue one in college algebra we call exponential decay, because it's decaying very rapidly. So notice how the limits change, right? On the blue one, as you go out to the right, this time the function heads to 0. But as you go to the left towards negative infinity, the function grows and gets bigger and bigger and becomes infinite. So it's like they switch places, right? It's like what the red one did, the blue one does, but opposite. Questions at all? Exponential functions, the way they look, the general behavior, we're happy?
So it's just the opposite, right? If it's less than 1, it would be the blue.
The blue, yeah.
And then it would switch from 0 and infinity, and then for the red.
I think if you just remember what the graphs look like, it's kind of easier to figure out what the limit is. So as long as you know that it looks like the blue one, then to the right it goes to 0 and to the left it goes to infinity. If it's the red one, then as you go to the left it goes to 0 and to the right it goes to infinity. Okay, now back in college algebra, you learn all of these properties of exponents. And we've worked a little bit with this, but I just want to remind you of what the properties are. And that is, when you deal with exponents, if you have something raised to a power times something raised to another power, so this is multiplication happening here between these, then you add the exponents. If you have division, then you subtract the exponents. If you have something to a power, then raise it to another power, you multiply the exponents. And if you have two things being multiplied and you raise all of that to a power, the power can be applied to each one of them. So these are all just properties of exponents. You might even learn that before college algebra. That might be like in an intermediate algebra class or high school or something. So this is just to remind you some of the properties of exponents. And that's it. Okay, that's all I'm saying about that. Now, 3.2 talks about inverse functions and specifically logarithms. So in college algebra, the first thing you do is you learn about these exponential functions, a to the x. And we just looked at those. And then you're told, you know what? Each of these functions has an inverse function, which is basically a function that undoes that function. And we call those logarithms or logarithmic functions. And so when we study that in college algebra, we say, hey, each of these logarithmic functions, again, has a graph. And everyone here needs to be familiar with what the logarithmic functions look like when you graph them, because they're not the same as the exponentials. They look different. So let's take a look at them. So if you have a logarithmic function, all logarithmic functions can be written log, and then you put the base here, a of x. That's the way we write a logarithmic function. And again, we pay attention to the a. We have two different scenarios. If a is bigger than 1 and if a is less than 1 and greater than 0. There's two different cases on the way the graph looks. What you're looking at here in red is what happens when a is greater than 1. So if a is greater than 1, the graph goes up and it keeps going. Okay, so this keeps growing. It's hard to see it, but this does keep growing. It's slow, but it grows and grows and grows, but it's just very slow, but it is going up. So as you go to infinity, if you move to the right, the function is headed upward to infinity. Does that make sense, this limit right here? Now, when you go to the left, we have a problem, because if you, again, go back to college algebra, you are never allowed to plug a negative number into a logarithm. So there are domain restrictions when it comes to logarithms, that this in here can never be, well, I should put it this way. It should always be a positive number. You can't plug a negative into a log, and you can't plug 0 into a log. Okay, it's undefined. It's kind of like trying to plug in a negative into a square root. Okay, the logarithm cannot handle negative numbers. You can even check it if you go on your calculator and you try and do the log of a negative number, you get an error. That's because there's a domain restriction. So I cannot talk about what happens as we go to the left. That doesn't make sense. The most we can go is approach 0. So remember, here's 0. We can talk about what happens when you approach 0 from the right-hand side. And you all see that as we approach 0, that the logarithmic function starts diving down and it heads towards negative infinity. Y'all see that from the picture, that it's just taking off and going down? So for the logarithmic function, with a being greater than 1, we have, as you go to the right, it goes up. And as you go to the left, you approach 0 and the function dives down to negative infinity. Now, what happens if I change this and I talk about when a is less than 1 instead of greater than 1? What's it going to look like? So here it is. So it's a reflection over the x-axis. And so when you look at this, you can see that as we go to the left, as we approach 0, right? As we go to the left and approach 0, it takes off to infinity. And as we go to the right, where's this headed? Where's that headed over there?
Negative.
It's headed down to negative infinity. And that's what it says right here. All right. So again, this is just a recap of what exponential functions look like, what logarithmic functions look like. All right, next thing. Properties of logarithms. So you might remember this in college algebra. You were given these logarithmic expressions and you were asked to like condense them or expand them. Do you remember that at all? It was like it was a section usually towards the end of the semester in college algebra where you're given some expression. I'll just give you an example.
Yeah,
you're given like
members.
Yeah, like something like this. You're asked to like expand this. And so you use these properties that, like this property here says, if you have two things being multiplied, that you can split it into 2 logs. So I can see I have multiplication here. So I can split this into 2 logs with addition between them. By the way, I put a line through here. I'm not saying product. I'm not saying product rule. We're not taking a derivative. This is just properties of logs I'm showing you, right? We're not talking about derivatives at all right now. So there's just a property of logarithms that you can always split it into 2 if you have multiplication inside. And then if you have division inside, you can split it into 2 with subtraction in between them. And this property is really nice. If you have x to a power, the power can come out in front of the log. That's what this is saying. So if I continue with the problem I was just working on here, I can take that 2 and drop it out front, and I can take that 3 and drop it out front to make this 2 log base 4 of x plus 3 log base, oops, I forgot to put the base here, base 4 of y. So that would be the expanded version of this logarithm. So again, this is not about me going and reteaching this. This is about me reminding you of these properties of logs that you learned in college algebra. We will at some points need to grab these and use these properties. All right. So when I do it, I don't want you to be like, what was that? Okay. So I'm reminding you now. Questions?
We're we're expected to know like what to do when the bases and stuff like that are different too, right?
When the bases are different?
Yeah, when like it's like log, base 4, and then the other one's like log base 10. Like you can't really add them together or something like that.
That's right. They would not be, you can't add logs together that don't have the same base.
Right.
Yeah, that would be expected that you know that.
Okay, just making sure.
Was that another comment? I'm sorry, I didn't hear that.
I said you can use the change of base formula.
Yeah, so there is a change of base formula, which is, I'm going to show you that in just a moment. It's down here a little further.
Yeah, just wanted to make sure.
Okay, so when it comes to the base of a logarithm, right, or the base of an exponential function, we've been talking about this a, right? And this a can be any positive number. It could be greater than 1 or less than 1, but it has to be positive. So in college algebra, you learn about a very special base. There's a very special positive number, and it is called e, right? Remember learning about this irrational number called e? And we say that, well, e is like the number pi. It's an actual number, but we use a letter to represent it. E is approximately 2.718. It's about 2.718. And so if we use that base here, we get e to the x, which I know you saw in college algebra. And this one specific exponential function is called the natural exponential function. And do y'all remember seeing that? And I know you have, Res.
Yes.
You saw that in college algebra.
They have like interest rates and other stuff.
Yeah, like interest, right? Simple interest and things like that. This thing, e to the x, came up. And I know when you're learning it, you're just like, okay, whatever, e to the x, sure, whatever, right? It's called the natural exponential function. I'm curious, does anybody remember their professors telling them why it's called the natural exponential function? Like e is just a number, right? It's just a number. I mean, you could use 2 here, right? 2 to the x or 5 to the x or any number that you want, as long as it's positive. So there's an infinite number of exponential functions, but this one in particular, we call the natural exponential function. No one remembers the professor saying why or anything?
The professor didn't tell us for sure.
The what?
I thought it was like because
It appears in nature.
someone said that there's a nature of it, right? Is that what someone just said a second ago?
Yeah, I mean, obviously it's important because we're calling it the natural exponential function, right? So there's something like inherently good about this function that makes us want to differentiate it from every other function by calling it the natural one, right?
Yeah, that
So,
one like be applied to a bunch of different stuff. I remember that portion, but I don't remember everything. So let's just go with no.
okay, so I'm going to explain why. Not yet. Just hang tight. I'm going to explain why it is called the natural exponential function, and it is a huge result. All right, but I'm not ready to tell you yet. All right. For now, we're just going to say, oh yeah, I remember the natural exponential function. Then after you learn about that, you say, well, what about its inverse? What is the inverse of this function? Well, it must be a logarithm, right?
Log, yeah.
And it's the logarithm that has the same base e, right? So this log base e is the inverse of this function. And this is such a special function that we name it the natural log function. All right, again, natural. It's something special about it. And it's so special, we even give it its own notation. We don't even write log base e of x anymore. We write ln x, right? That's what we write. So this means this, okay? Now, I'm not going to get into a long drawn out story. I've always hated that we use this notation because it confuses the hell out of students, right? I wish all logarithms were always written explicitly with their bases, like log base 4, log base 7. And if you want to use e, then write log base e. Don't write this. Historically, though, the reason is because back before computers, when research papers were being done, like people were doing a lot of research in science, different sciences, the natural logarithm function came up so many times that you might be writing a paper that you have to put that natural log in there maybe like 20,000 times within the paper. We're talking about like scientific research, right? So back before computers, when they were using typewriters, it was very difficult to do subscripting. If anyone here has ever used like an old school typewriter, if you actually had to write log base e of x, like type it, you would type, you know, log, then you'd have to stop and like turn the little drum and then hit E and then turn the drum back and then continue typing. And if you have to do that like, you know, 20,000 times in a paper, it's a pain in the ass. And in typewriter, you mess up and you have to get white out, it's a mess. So we just like as a convention said, let's just do ln x because you can type that without ever stopping. Does that make sense? It's just, you just keep going.
So does ln just stand for log natural?
It's French, yes. Logarithm naturel, right? The French like to flip things over. So it is from French. Yep, but it stands for, a lot of people think that this stands for I, like it's IN. That's not IN, it's LN, and it stands for logarithm natural. Exactly. Okay. All right, so we continue. So in college algebra, we learned about exponential functions, we learned about logarithms, then we learned about a very special exponential function, the natural exponential function. Then we learned about its inverse, which is the natural log. And then we're told that there's all these properties between these two functions because they are inverses. One property is that when you put natural log and e together, they wipe each other out and it spits out whatever was up here. So like, for example, if you do natural log of e squared, the answer is 2, right? It's just whatever the exponent is, pops out. And this should not be like crazy to you because what's happening here is what we should expect with all functions. If you have a function that starts off, takes a number in, let's say 2, spits it out over here as some number, then the inverse function should take it back where? Where should that number go back to?
There.
Back to 2, right? So if 2 goes through f, and comes out something, the inverse function should take that answer right back to where it came from. That's what inverse functions do. So this is like saying, oh, I'm going to plug 2 into the e, right? But then I'm going to hit that answer with the natural log. So that should take the 2 right back to where it came from. Now you could reverse it, and that's what this next property is, which is if you do e raised to the natural log of, let's say 4, this should spit out 4. And that's the same thing. You're composing 2 inverse functions together, and so they kill each other off. Okay, those are properties from Cal 1. I mean, sorry, from college algebra.
The number has to be greater than 0.
Pardon me?
The number has to be greater than 0.
Yes, why? Why for here does it have to be greater than 0? Because you're plugging into the log, right? And logs can't accept negative numbers or 0. You can only plug in positive numbers, which is why we have that little restriction here.
Thank you.
All right, e to the 0 is 1. Everyone should know this. Any number to the 0 is 1. Okay, so I think that's just a result. Have y'all ever wondered why any number to the 0 is 1? Have y'all ever wondered why that is? I can show you something. It may not convince you, but it might help you. Like let's just look at this. What about 2 cubed? Right, that's an 8, right? Okay, let's go 2 squared. What's that? 4. Let's go 2 to the first power. What's that? 2. What's happening every time we go down here? What's
It's cut.
happening?
Down by half.
Half it.
Cutting it in half each time, right? Half of that. So what should the next one be? What's half of that?
1.
Should be 1, right? And that's what 2 to the 0 would be, right? So 3, 2, 1, 0. And then check this out. What would happen if you do it again? What would be the next one? If we did half of 1, what would it be?
1/2.
A half. Now, does it make sense? Because according to this pattern over here, it should be 2 to the negative 1 should be here, right?
Mm.
But isn't 2 to the negative 1 1/2? That's what it means, right? 2 to the negative 1 is the same as 1 over 2 to the 1. And if we did it again, what would half of half be? 4,
Fourth.
right? And that should be 2 to the negative 2, which it is. Because 2 to the negative 2 is 1 over 2 squared, which is 1/4. This is not a proof. It's just showing you that 1 does kind of naturally happen here, like in the pattern of things. So e to the 0 is 1, all right? We should know that. This is a big one. Everyone should know that. Natural log of 1 is 0. Here's the way I like to look at these two together. If your function, if this is e to the x, and this is the inverse function, natural log of x, then we know that from this example here, if we start with 0, we know that e to the 0 is going to give me 1. So where should the inverse function take 1 back to? 1 should go back to 0, right? So if I do natural log of that 1, it should go back to 0. So that's why this is true. All right, and then this last one, natural log of e is 1. That's because the exponent here on the e is 1. And it's actually this first property right here. See, natural log of e to the x is x. Well, if x is 1, then the answer is 1. All right, are these is this kind of coming back a little bit? Like, yeah, I remember kind of seeing this.
Mm-hmm.
I have a bit of a weird question.
Okay,
You know, you could transfer a logarithm to an exponent, right? You can convert it.
yes,
So you can have negative exponents, but you can't have a negative log.
that's right. You can raise a number to, you can raise something to a negative number, but you can't take log of a negative number.
That just seems weird to me a little bit.
Seems weird. Okay, well, give me a number. Just give me a simple number. What do you want?
2.
2. Okay, let's look at 2 to the x. Okay, what happens if I graph this? Well,
It depends what x is.
I know, but in terms of this is like an exponential function, right?
Mm-hmm.
And that number there is a, and it's greater than 1. So we should expect exponential growth. Do you agree?
Mm-hmm.
Okay. So if I look at the inputs, can I plug in negative numbers into this graph or into this function?
Yes.
Yeah, I can plug negative numbers in. So if I look at the domain of that, then I can have positives and negatives in here. Agreed?
Yes.
Now, when I send them through the function 2 to the x, can I get negatives out? Look at your graph, look at your outputs. Aren't they all above the x-axis?
Well, if it was to the third power, like -3, wouldn't it have like oscillation kind of?
2 to the negative 3 is equal to 1 over 2 cubed, which is 1/8. So even though you're plugging in a negative, you're not going to get a negative answer out. You're going to get a 1/8 out. No matter what number you plug in, -1, -2, -3, you're always going to get a positive number out because these are all above the x-axis, aren't they?
Mm-hmm.
So no matter what happens, whether or not I plug in a positive or negative here, I'm always going to get a positive number out. Do you understand that?
Mm-hmm.
So the inverse function, which takes you back, log base 2 of x, I can't plug negatives in. See, negatives don't exist over here. So if you try and plug a negative into this, it has no idea where to take it because there's nothing that actually went to a negative number. So it's impossible for that to happen,
Okay.
which is why you can't plug negatives into logs.
Okay, because I was thinking of the function x to the third power, and you know how it switches
Oh,
That's
okay.
why,
Well, you're
yeah, I'm
talking.
getting mixed up. Yeah.
Okay, yeah, good. I'm glad you brought that up. So you're thinking about this function.
Yeah.
That's not an exponential function.
It's not.
This is a polynomial function. The difference between an exponential function and a polynomial is where the variable appears. If the variable is down in the base, it's a polynomial. If the variable is up in the exponent, we call it a exponential function. That's where the name comes from. It's where the variable appears.
Okay.
Do you see the difference between the two?
Yeah.
So these two functions right here are completely different, right? This, if you graph it, this one, if we graph it, looks like this. Okay. This, if you graph it, looks like this.
Okay. Yeah. I get it
Understand?
now. Yeah.
Got it? Okay, good. I'm glad you brought up that question because I didn't mention that at the beginning. Like we must distinguish between exponential functions and polynomials. They are not the same. And it's all about where the variable appears.
Okay. That helps a lot. Thank you.
Okay, good, good. Okay, go ahead.
Be, positive because we never get to 0. Is that?
Yeah, and you never get to 0. That's right. You can get real close, but you'll never get there. Okay, so now if you've ever looked at your calculator usually only has a natural log key. Depends on your calculator, but a lot of calculators only have a natural log key. It'll be a key on your calculator that'll just say ln on it or something like that. And so if you're trying to figure out in college algebra, if you're trying to figure out what log base 4 of 8 is, then there's no key for the log base 4. But this change of base formula is a way that you can find the log of anything using your calculator. So if you have log base a of x, according to this formula from college algebra, this would become the natural log of 8 divided by the natural log of 4, just following that formula. And then you can use your calculator. So that's why your calculator only has one key on it, because with logarithms, you only need one key to do all logarithms. So that's an important formula from college algebra. Just make sure you're aware of that. Okay.
Mm-hmm.
All right. And that's it. Okay, that's the crash course review of exponential and logarithmic functions. Now this is not algebra, this is calculus. And what we're doing here and what we're learning right now is derivatives, right? We've spent all this time, invested all this energy into finding derivatives. Right now, you should be comfortable taking derivatives of there's a tremendous number of functions you should be able to take derivative of now, right? You can do sine, cosine, tangent, all the trig functions you know derivatives of. You know how to do x to different powers. You know how to do product rule, quotient rule, chain rule. You've got all that stuff, right? It's all here. But we have conveniently stayed away from two particular functions. We have not talked about exponential and we have not talked about log. We have not done those yet, all right? And now it's time to talk about what is the derivative of the exponential function. And then after that, we'll talk about what the derivative of log is, okay? So you ready for this? You want to know why they call it the natural exponential function, right? You want to know why?
Yeah.
Here's why. Okay, so I'm going to get a different. So here's kind of a quick recap of what we've learned in this class, real quick. If I were to just let me start with some function, x squared. Now that is not an exponential function, right? That's a polynomial. We know what that graph looks like. If I graph it, it's just a parabola, it opens up, right? It does. We also have learned in this class what the derivative of that is. The derivative of that function should be 2 times x, right? So if I were to go right now and pick some random point, let me just pick a random point. I'm going to pick 3. And I go up here, what would happen if I plugged 3 into this function? How high up would I be?
9.
What's my value here?
9.
9, right? That's 9. So that point on the graph is the 0.39. There's no calculus here, right? That's just algebra. Plug in 3, square it, you get 9. Yes, everyone good? Now let me ask you, what's the slope of the tangent line there? What's the slope of that line? Well, then you would go to this, wouldn't you? Because the derivative is what tells you what the slope of the tangent line is. And you would plug in what for x?
3.
3, okay? So the derivative at 3 would be 2 times 3, which is 6, right? So the slope of that line is 6. That's what we've kind of, all this work we've done, that's the geometry of what we're able to do now, right? If we have a function, we can go to any point and we should be able to find the slope of the tangent line. Yes? So mathematicians, physicists, chemists, scientists, for a long, long time, were trying to figure out, is there a function? Okay, so the question was this: is there some function out there that when you graph it, okay, I'm just going to just throw a random graph in here, okay? They said, you know, is there a function f of x that when you graph it, it has this very unique property? And here's the property: that when you go to some point, let's say, I don't know, 3, and you plug it in, you're going to get some y value out here, right? In the previous problem, it was 9, wasn't it? But generally, I don't know what this would be, right? That's supposed to be a question mark. That's a question mark, right? In fact, isn't that just the function's value at 3? I still don't know what the function is, but that's the value of the function at 3. Got it? So far, the question was, is there a function out there that when you plug in 3, you get some value? But also, when you look at the derivative, okay, when you look at the derivative, that value that you get at 3 is also the function's value. In other words, the slope of this tangent line is just the y coordinate on the graph. Let me see if I can make that make more sense. Is the slope of this line equal to this y coordinate? No, 6 is not equal to 9. I wonder if there's a function that when you go to 3, this slope is actually equal to the y value also. And is there a function that would happen at every point? At every point you could ever go to, you go to any point you want, I'll call it A. I go up here, and whatever that y value is also the slope of the tangent line. Does that make sense? Like
Identity function?
Well, okay, so the identity function won't work. And the identity function won't work because, well, I'll show you in a second. But does everyone understand the thing that we were kind of looking for? Like, is there a function that the slope of the tangent line at any given point is equal to the y coordinate at that point? That's what we wondered. Is there a function out there that does that, right? Does it exist? Now, it was just proposed, maybe it's the identity function. The identity function is the diagonal function. That's f of x equals x, right? Now, what's the derivative of this function? 1, always,
1.
right? Now, that means that if I go here, let's go to the point 3. What does this function spit out when I am at 3? What does it spit out?
3.
3. Okay, but what's the slope of the tangent line there?
1.
1. Are they the same?
No.
No. But we're trying to see, is there a function out there that would have that property? These aren't equal. So we wondered and wondered and wondered, and we looked and looked and looked and looked, and we finally found it. All right. And it is, lo and behold, it is this one. It's e to the x. That is the one. And it's the only one. It's unique. There are no others that do it. This is the only one. So we can't explain why it is the only one. It just kind of naturally is. We have no other explanation other than to say that's the one, okay? So it became our natural exponential function. It's the one that has this beautiful property that if you ever want to know the slope of the tangent line at any point, all you have to know is the y-coordinate. If you know the y-coordinate, you know the slope of tangent line. But moreover, doesn't it just mean this? This is the big profound thing. Doesn't it just mean that the derivative of this function is just the output of this function, which is just the function itself? Does that make sense? If this represents the y value coming out of the function, and I'm telling you that the slope of the tangent line is equal to that y value, that's the slope, then what I'm telling you is that the function f of x equals e to the x, when you take its derivative, you get e to the x. It is itself. It is its own derivative. And that's the major takeaway from 3.3, is that, where is it? Hold on, it's further on. It's right here. I'll get back to it. It's too distracting that way. Is that not awesome or what? I can't prove it to you, okay? I'm sorry, I can't prove that it's true. You take Cal 2, I'll prove it to you. But I can't, here I just have to have you take it on faith, okay? You just have to believe me when I tell you that e to the x is the only function that is its own derivative, all right?
So does that mean that all of the ln functions, all their slopes are just equal to the x value?
That all their, wait, say
Like
again?
like the inverse of this, is it just since this is equal to the y, is that just equal to the x?
Are you asking me that if you look at the natural log function and graph it,
Yes.
are you talking about the slopes of the tangent lines on the natural log?
Yes.
Like, are you asking me, are those also just equal to the y value there?
Not the y, but since this is the inverse, would it be the x?
Unfortunately, no, it is not. Yeah, because the inverse just, it behaves a different way. The relationship that we have doesn't translate to the inverse. It only works for this function. If it worked for the inverse too, then we'd have two different functions that have like the similar property, but it only works for e to the x. Now, it took a long time for us to figure this out, okay? I mean, and the reason why it's so vitally important is because it's almost like, here's the only way I could compare this that maybe would make sense. Imagine you're driving your car, right? And you're driving and you look down at the speedometer, okay? And it says you're going 20 miles an hour. And at that exact moment, you've gone 20 miles. And then you look at your speedometer a little bit later, and now it says you're going 30 miles per hour. And at that moment, you've traveled 30 miles. So at every moment in time, your speed is actually equal to how far you've gone. So if you look down, you see 80 miles an hour, you've gone 80 miles. If you look down, you see 1 mile per hour, you've gone 1 mile. There is only one function that behaves that way, where the rate of change is equal to the function's value for every value of x, and it's e to the x. Okay, take it on faith. I can kind of, no, I won't show you. I'm not going to show you. I'm not going to. No, don't, stay away.
What about if we have extra time after, not extra time, but you know, after class, like that?
Maybe. Okay, so here's the big takeaway, all right? If f of x equals e to the x, then f prime of x equals e to the x. Memorize it. It's not hard to memorize, right? I mean, derivative of e to the x is itself, right? That's pretty simple to memorize. It's not like having to memorize the derivative of sine of x was cosine of x, or the derivative of cosine of x is negative sine of x, or the derivative of tangent of x is secant squared x. Like, it's not complicated like that. This is the only one that behaves this way. Okay, so that's that we're gonna take on faith and we're gonna be happy about it. Now, what about if it's not? What if it's actually like a to the x? And like generally speaking, it's not this very special base. What if it's just some other base? Then what's the derivative, right? Well, let me tell you what it is. And again, you're going to take it on faith. The derivative of a to the x is itself, okay, and multiplied times the natural log of a. Now I'm going to give you a specific example of this one. Let's say we have the function f of x equals 2 to the x. Then, according to what I just said, the derivative of this will be itself 2 to the x. So it's almost behaving like this. But then you have to tack on to it times natural log of what? Natural log of a. But what's a here for us?
Is, yeah.
2, right? And just keep in mind, everyone, natural log of 2 is just a number. You could do that on your calculator. Natural log of 2 would be a number. So this is really, it's like for 2 to the x, its derivative is almost itself. It's almost the same thing, except you have to scale it, so it's not going to exactly be the same. Like this answer is going to be like shifted off just a little bit. All right.
Change it.
Pardon me?
We don't have to change it or anything like that.
Change it to what?
Like, can't we change something like an exponential into a log?
No.
Right? I don't remember. There's something going on in my head.
No,
Never
no,
mind.
this is it. Natural log of 2 is just a number, and it's a number in front of a function.
Okay.
Okay, so these are the two big results so far. Is, what is the derivative of e to the x? It's itself. What's the derivative of a to the x? Well, it's itself times this natural log of a. Hey, out of curiosity, what would have happened if we would have used this formula right here with e there? If that would have been an e, then that would have been an e, and then I would have natural log of e. But do y'all remember what natural log of e is?
1.
It's 1. So do you see that this actually does work and it creates this formula up here? Now, you don't need to necessarily pay too much attention to that. I'm just showing you that the formula actually, the one in red is actually more general than the one in black. The black is a specific case. The red is all cases. Okay, so now we know derivative of e to the x and we know derivative of all exponential functions. What do you think is going to be next?
Logarithms.
Let's talk about logs, okay? So let's start with the natural log. If f of x is the natural log of x, then its derivative, you ready for this? Here's its derivative. You're not even gonna, you're gonna be like, what? Because it doesn't even seem like it should be this, but it is. It's just 1 over x. That's it. 1 divided by x. So Benjamin, wait, Cody or Benjamin, who was asking me about, is the slope of the tangent line on natural log just the x coordinate? Was that Cody?
It was me.
It's almost, right? What is it? It's not the x coordinate, it's the reciprocal of the x coordinate. So if you plug in 2, it's actually 1/2. If you plug in 3, it's actually 1/3. So it's not quite, but that was a good conjecture. A conjecture is like a guess. Okay, that's a good guess as to what it would be.
What if there's a number right in front of a natural log?
We'll get to that. We'll get to that. Okay, so that now is what the derivative of the natural log is. But what about in general? What's the derivative of any log? So that means a log with any base of x. Right? Well, here's what it is. Again, I'm telling you this, you're going to take it on faith and you're going to be happy. It is 1 over x. Hey, it's the same answer, right? 1 over x But next to the x, you have to do natural log of a. So it's 1 divided by x times the natural log of a, and that is the formula. Now these formulas are on your formula sheet. Okay, they're there. I just wanted to go through them, write them down, but let's go look at them on the formula sheet so you know where they are. Moving through here, derivatives. Where are you? There you all are. Okay, gonna zoom in on this. The derivative of e to the x is e to the x. The derivative of the natural log, now they put an absolute value of x here, but that's only because you can't plug negatives into natural log. So they're just being like playing it very safe here. So derivative of natural log of x is 1 over x. Okay, I just gave you all those two. And if you scroll to the right and look at the next two over here, this is the more general version. The derivative of a to the x is itself times natural log of a, and the derivative of log base a of x is 1 over x natural log a. So those are the 4 formulas I just gave you. They're in your formula sheet under exponential and logarithmic functions. And I've got great news now. Okay, the great news is we are done in this class as far as learning derivatives of functions. Like in terms of, there are no new functions we're going to go learn the derivatives of. We've got, you know, all the trig functions done, right? All 6 trig functions, we know their derivatives. Exponential logs, we have those taken care of. And then anything with powers and stuff like that, we can take care of. What we're not going to do are inverse trig functions or hyperbolic trig functions because those come in Cal 2. That's usually what you start Cal 2 with. Okay, so there's still more to look at, but that'll come in Cal 2.
Is
We're done.
I'm sorry.
What?
Is this function, not this function, is this rule or whatever, it just looks like this one? Are those somehow related? Because it just reminds me of that.
What does?
This, the 1 over n plus 1 x to the n plus 1 plus c.
What reminds you of that?
The 1 over
one?
x times ln a, yeah.
Not
just
really. No, because these are completely different types of functions. What you're looking at is the power rule for antiderivatives, and that's not, that doesn't correlate here with the log, the derivative of the log.
It's just a random thought. They just look similar to me and me.
Yeah, there's a little similarity there, but it's not.
Okay.
Okay, are y'all ready? You ready? Here we go. So now that you know this, what can I ask you? Well, how about this? Find y prime. So I'm going to give you a function. Y equals x squared e to the x. So I want the derivative of that. So we have the new player, right? This is the new kid in town right here, e to the x. Everything else is the stuff we already know. So what do we see happening between those two functions?
Product rule.
Product rule, right? So we have to do the product rule. So if I want the derivative of this, I've got to take the derivative of the first one, which would be 2x, times e to the x. Okay, so I'm doing f prime g, and then plus now the derivative of e to the x, which is
E to the x.
itself, right? E to the x, and then times what?
X squared.
X squared. Okay, does everyone see the product rule here? Yeah, everyone see the product rule? Now I'm done, that's the raw derivative, but I do want to point out that both of them have an x and both of them have an e to the x. So I am allowed to factor. I could pull an x e to the x out of both of these. So if I pull an x e to the x out of the first one, I get a 2. If I pull an x and an e to the x out of the second one, I'll be left with an x. So that is equivalent, all right? And as we're now moving into the later part of this class, these little algebra things are going to become more important that we're okay with, all right? That we can do little factorings and things like that.
If those were put in parentheses, like would it be different? You couldn't pull it out? because it would be like that one equation plus a different equation. You couldn't factor it out like that.
If this was in parentheses and this was in parentheses?
Yeah.
No, because the plus sign is like a +1, and that would distribute through, and then the parentheses are gone and nothing changes. And then there's like a 1 here that distributes through, and it's like all the parentheses just disappear.
Okay.
Yeah. Okay, let's do another one. So find y prime. You know what? I'm out of room on this page. Find y prime. If I tell you that y is equal to sine squared of e to the x plus x. Okay, so all that really is happening here today is I've now introduced these new functions that we can take derivatives of. And now we're just going to start throwing them into what we already know. And so we start to get these, you know, derivatives like we did on the test, but now we've got this new thing we have to pay attention to. So what do y'all see happening here? Why don't I give everyone a minute? I'll just give everyone a minute to see if you can figure this out on your own, and then I'll go through it, okay? I'm going to be calling on somebody randomly here in a second. All right, I think that's enough time. All right, how about Emmanuel?
Hello.
How do you feel about this one?
Feel like it's simple enough.
Okay, go for it. What do you got?
So since I noticed the 2 squared near the sign, I put it like separated from the parentheses and then took it to the front.
Okay, so you're looking at this as being sine of e to the x plus x, but all of that squared, like that kind of, and then you're going to pull the 2 out front when you take derivative?
Yes.
That's right. Okay, so the 2 is going to come out first, and then it's what?
Sine e, then all the stuff in the inside.
Okay, and that's all raised to the first power, right? Even though, I mean, like, we don't need to write the first power, but had this been like a 4, then we would have a cubed here or something, right?
Correct.
Okay. Okay, and then what do you got?
And after that, I was going to do change the sign into a cosine.
Cosine. So we're doing chain rule here. We've done the 2. Now we're moving into the sine, which becomes cosine of what?
Of everything inside as well.
Good, good. Are you done?
Not yet. Then you have to deal with the stuff that's inside now.
Okay, so that would be what?
Since
So the derivative of the inside.
derivative is going to be, since it's an EX, it will still be EX.
Yeah,
right?
VX, good.
And plus 1.
Plus 1. Now you do need that in parentheses. So we could do these separately because there's addition between them. Good job. That was perfect. Good. All right. So look, in the previous parts of this class, leading up to exam 2, this has all been about you learning how to do derivatives in the rules, product chain, product quotient chain, all that. That's like you're learning how to crawl, right? Now we're walking. Okay. So now I'm expecting that you can all do this with relative, like at a faster pace. We can't go and break every single problem down into oh, f prime g plus g prime f, and write all the little details out. Maybe you need to do that still on the side, but as I'm presenting it, I'm going to be moving through it faster. All right. Okay, next one. Let's do, how about this? Find y prime. Okay, y equals, how about this one? X e to the sine x. I'll give you a minute. Okay. Who do we have here? Laura here? Laura?
Yeah,
Laura?
I'm here.
Okay, Laura, how's this going?
Good, I think.
Okay, all right. So what do you see?
I see the product rule, and then I wasn't too sure, but I think you'd use the chain rule also.
Okay, yes, that is correct. All right, so take me through this. You're going to do ultimately the product rule, okay, which would be what?
It would be 1 times e to the sine x.
Okay, good. That's f prime g plus,
Plus e to the sine x times cosine x times x.
perfect. That makes sense to you, Laura?
Mhm.
Obviously it does. Okay, so does everyone grasp what just happened? We did this like an f and a g. So this is f prime times g plus this whole thing is g prime and then times f. I think the part of this that's the hardest is this g prime. So the way Laura looked at this is you have e raised to something, right? So what is the derivative of e to anything? Well, it's itself. So e to the sine x. But chain rule then says you must take derivative of what's up here, which would be the derivative of sine, which is cosine of x. And then finish off the product rule by putting the f here out on the backside. Who needs clarification on that?
I do, just a little bit.
Okay, so are you okay with the fact that when you have e raised to anything, the derivative of e to something would be just itself?
Yes, sir.
Okay, and then once you've done that, you have to look at what's up here and take the derivative of that, which is where the cosine comes from. So this is a chain rule happening on this piece, the yellow and the blue.
Okay.
Or you sound like you're just being agreeable.
Yeah, a little bit.
Okay, so what if I had this? What if I said cosine of sine x and I ask you to take the derivative of this? You start with the cosine, right?
Mhm.
And you'd put negative sine of sine x first.
Yes.
Okay, and then you'd multiply that times what?
Times cosine.
Cosine, right? So it's like the outer function was the cosine, and that's why you did that, right?
Mhm.
And then once you were done doing that, then you moved to the inner function, which was this one. You took derivative there and put it here. Yes?
Yes.
Look at this the same way, but it's like e is the outer function, like the cosine was. So the first thing you're doing is you're saying, what's derivative of cosine? Well, negative sine. Well, what's the derivative of e? to something, it's e to that something. So this is like e raised to the same thing. And then once you've done that part, then you move to the exponent and you take derivative of that, which is where the cosine comes from.
So why don't we see it like opposite, like how we do with like sine squared, where we would move the 2 out instead of.
Very good question. Yeah, so, okay, I see what you're getting at, Natalie. So what Natalie is saying is, she's seeing this, right? And there's this instinct where I think what she wants to do is bring the sine x out. And then make this, I don't know, maybe sine x minus 1 on top or something like that. Like where you bring the power out. Okay, very good question. The reason why you don't do this is because this is not x to the n. You only bring out powers when the power here is a number, then you bring out the n, then the x, and then you subtract 1. So because this is a number and the variable's down in the bottom, you use power rule. But if the bottom is a number, remember e is a number, and the power has an x in it, you do not use this rule ever.
Okay, now it makes sense.
Let me show you one more example. 2 to the x. A very common mistake I see with this is that people will say, oh, I'm going to bring the x out and then put 2 to the x minus 1. Does everyone see what I've done here? Pulled the power out, subtracted 1 from the power. This is completely wrong. And the reason why is because this does not look like that. The x is in the wrong place. The x is not in the base, it's on the exponent. So the true derivative of this would be itself times natural log of a, following the formula that I just gave you. Does that help, Natalie?
Yes, sir.
Okay, good. Good. All right, we need to do another one. How about x to the 4th natural log of sine x? Go ahead. If you get that one and you want something else to practice, those are 2 different problems. All right. Austin, you ready?
Yes, sir.
How'd you do on that first one?
I think I got it.
Okay, go ahead.
So start with a product rule, and it's going to be I got 4x times natural log of sine x.
4x cubed.
Oh, cubed, yeah, sorry.
Yep. Okay.
and then plus, and then
Here's
this
the tricky part, right?
chain rule.
Okay.
And I got 1 over sine x times cosine x times x to the 4th.
Perfect. Okay, so let's see what happened here. Product rule, take derivative of the first one here, 4x cubed times the second one. Plus, now Austin's looking at this natural log of sine x like a chain rule. There's the outside function natural log, inside function sine. Austin's saying, okay, the derivative of natural log of something is 1 over it. So he puts 1 over sine x. And then says, now what's the derivative of sine? And that's cosine. And then the x to the 4th is from the beginning. Now, you could go a little further with this. Nah, I'm happy with that for now, but just to point out that you could write that as cotangent x, because cosine over sine is cotangent. Any questions? How about for these two? Did anybody get this first one?
I tried it.
Isn't the ln derivative is 1 over x already?
The derivative of natural log of something is 1 over it. 1 over whatever that something is, okay? So our formula is this: the derivative of natural log of x is just 1 over x, okay? But if this in here is something other than x, like, I don't know, natural log of a yellow blob, the answer is 1 over the yellow blob, right?
Got it. Thank you.
So since you brought it up, what would this be? The derivative natural log of this yellow blob would be 1 over what?
1 over x.
1 over x. Now chain rule times, now you have to take derivative of what's in here. Can somebody tell me what derivative of that is?
I think it'd be negative 1 over x squared.
Negative 1 over x squared. How'd you do that?
I just use the quotient rule.
You use quotient rule? Okay. You can use quotient rule, right? There's a faster way. Look, everyone, this is really x to the negative 1, isn't it? Isn't that what 1 over x really means? X to negative 1. Now, if you had to take derivative of that, you'd bring the negative 1 out, and then you'd subtract 1 from the power, you get x to negative 2. And now if you rewrite that, leaving the negative 1 on top and dropping the x to negative 2 down as an x squared, you'd get this, which is the exact same thing that Elise got, which is fine. I personally prefer to do it this way, but you get the same answer. Now we're not done. We can clean this up. 1 over x is x times negative 1 over x squared, which is really negative x over x squared. Just slide that x up top. And let's cancel one of the x's. So we get negative 1 over x. Everyone okay with the fact that just one of those x's cancels? Any questions here? I'm going to show you something kind of cool.
Will that stay true no matter, like, so say that was natural log of like 15 over x, would it just become, the answer would be negative 15 over x?
That's a good question. Maybe, maybe not. Let's see. I want you to notice something on this problem. I'm going to move it here for a second. Do you all agree that this is just the same as this problem? Just rewriting 1 over x like this. You all agree? That's true? Same problem? Now, I want to go back to properties of logs. Where were they? That one right there. This says that if you have any log, doesn't matter what it is, could be the natural log, could be any log, and you have x to a power, you're allowed to bring the power out front. All right, that's what that says. The power can come out front. So I'm going to go back to that problem we were just looking at, and I'm going to notice that I have a power up here on the x. So I'm just going to drop that out front using properties of logs. This becomes negative natural log of just x now, because the power came out. I'm not taking a derivative. I'm just using a property of logs. And now if I have to take the derivative of, if I want to take derivative of this, the negative just stays out here as like a -1. And then I take the derivative of natural log of x, which is 1 over x. And that's the same answer. That just shows you there's like a different way you could have done that. So to answer your question, Austin, yes, if this would have been like 15 over x, you could use similar idea here and you would get -15 over x. Okay, how does that problem compare to this one over here? It's not the same problem, is it? No, right? That's different. This is a quotient rule. F is, the top function is 1, the bottom function is g. Or the bottom function, natural log of x is g. So if we want the derivative, we have to do the derivative of the top one, which is 0, times the bottom function, minus, what's the derivative of the bottom function?
1 over x.
1 over x, times the top function, which is just 1, all over the bottom function, natural log of x, the whole thing squared. And that becomes, let's see, that goes away. On top, we just get -1 over x, and then over natural log of x squared. And that answer is definitely different than this answer. So there's just like, you know, subtle differences between these two problems, but there's huge differences in their derivatives. Questions? I want to look real quick at the homework assignment for this. This is 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, 15, 17, 18. Oof, 18 is a beast. 20. Shit, that's a lot of problems. Okay, so look, these are really good problems. Just looking here. Yeah. This is good. This is good. Well, you have your work cut out for you. Because really, I mean, I've just introduced some new functions that you need to be able to take derivatives with now, right? So now the homework assignment for this, make sure you do it, all right? Make sure you do it twice if you have to, because you're going to get tested on all the rules again, but now with these new functions incorporated into it. So here's one. Y equals e to the ax cosine of bx. And here I'm telling you that a and b are just constants. I want you to find, you ready for this? Y double prime. I want the second derivative, which means you have to take derivative and then you have to take it again. I'll give you a minute, or I'm going to give you a couple of minutes. How about I give you about 5 minutes to see just how far you can get this? At least try and get the first derivative. I think what I'm going to do is start working it out, and then you can look to see if you're following what I'm doing. You can try and look at what I did and see if you can make sense out of where every piece came from. I haven't even started the second derivative, but I'm going to stop here and talk to you all in about a minute.
Hey, Professor. Why are we multiplying this with an A?
Are we what?
This right here, the very first step. I mean, I did get everything except that I multiply with A.
Okay.
Yeah, right there.
Does someone want to explain why there's an A there?
It's because A is a constant.
And it comes
Okay.
along for the right.
But where does it come from though?
It's
does
the
that A?
chain rule.
The chain rule. This A is the derivative of what?
A of x.
AX.
I
Okay,
messed
so
up.
Dilpreet, first thing you do is you take derivative of e to something, right? The derivative of e to anything is itself. Then you have to take derivative of what's here. But I told you a is a constant. So just imagine that this said like 4x. What would the derivative of 4x be?
4.
4. But it's ax, so the derivative of ax would just be a.
Okay, I just missed that accidentally.
You have to treat a and b like constants in the problem.
Got it. Thank you.
Good question. Okay, who else has a question on where any of this came from? Everyone okay with the negative sign bx?
I don't have a question about any of those, but did you want us to simplify that to be able to find the second derivative, or should we leave it the way that it was?
Well, yeah, you notice how I started to clean things up over here? Like I brought the a out in front, then I put the e to the ax here, and I brought the cosine bx here, and then over here I brought the b out front with the minus sign, and I brought the e to the ax out front. You see how I did that?
Mm-hmm.
I'm cleaning it up because I need to take derivative again, right? That's why I'm cleaning. So I think, you know, if all I wanted was the first derivative, you'd be fine here. But because we need a second derivative, I'm going to try and clean it up. In fact, I'm about to go a little bit further. Watch. This is kind of a nice critical step of the problem. I'm going to notice that both of these have an e to the ax in them. Right? Do y'all see how they both have an e to the ax? I can factor out an e to the ax, and I'll be left with a cosine of bx minus b sine of bx. So if you remove this and pull it out in front, then you would have this times all of the stuff that was left. Questions on that step? Now I'm going to do the derivative again. So my second derivative, I want everyone to pay attention here, product rule right there. I created that product when I pulled it out. But the reason why I think that's better, and pay attention to this, if you don't do this, then you're actually going to have two product rules you're going to have to do. If you leave it the way it was up here, you'll have to do a product rule here and here. Y'all see that there will be two products here? So I'm going to choose to do it this way, factor it out, and then take my derivative. Okay, so let's see, who's up here? Jean, are you here? Jean? Jean, no?
Yes, I'm here.
Okay, Jean, are you following or no?
I am.
Okay, so let's do product rule here. We'll treat this thing like F and this thing like G. Let's see if I can help you, you help me, whatever. Walk me through the product rule on this thing.
So the first one's just going to be e over ax.
E
and then,
raised to the E raised to the ax.
And then times a.
Times a, good. That's chain rule again, because you have to take derivative. What's up here? Keep going.
And then it'll be times that everything inside the parentheses, that big old string of.
Yeah, just there's G, right? Okay, good. Okay, now what?
And then it'll be the derivative of all that, which is
okay. Plus, right? Plus.
Yeah, plus.
Product. Okay, plus. Now you ready to take derivative? You can do these individually, Gene, because they're separated by subtraction. So, Gene, on this one, what are you going to do with this a that's out front?
Out front, that's a constant, so it's just going to be nothing.
Yeah, it'll just come here, right? It'll just come with us. Okay, and then now take derivative of cosine of bx. What do you get when you take derivative of cosine of bx?
Negative sine bx.
Bx. Almost done.
And then bx times b.
Times b. Y'all see that? You had the a, which was a constant out front. The derivative of all this, the a comes for the ride. Then you have derivative of cosine of something, which is negative sine of it. I need another parenthesis. And then you have to take derivative of what was inside the cosine. Derivative of bx is b, right, Dilpreet? Derivative of bx is b, okay? And Gene, we're done with this one, right? Then we're gonna go, you wanna keep going? I think you're gonna get it.
Yeah, okay. And then it will be just negative, negative, and then it'll be b, bring b along with the ride. Sine, we'll do cosine. Cosine bx, and then times just b.
There it is. That's your second derivative. It's ugly, but it is the second derivative. Oh, wait, hold on. We're not done. All of this, we have to remember what we were doing. I slowed down too much. So this was f prime times g plus all of that was g prime, but what do we still need out here?
We still need just times e powered of ax.
So there we go. Okay, f prime g plus g prime f. There's your derivative.
I think you're right about it being ugly.
Yeah. Yeah. So as you can see, I mean, this is one of the one of the more challenging problems in the homework, but it gives you a flavor for like just how much stuff can be involved. So highly recommend you do your homework for this. Now, I need you to stop when you're doing your homework. I need you to stop. Don't do anything past number 44. Stop at 44. I don't even know if 44 is on the homework list, but don't do anything past 44 because we have not talked about anything. We still have some more stuff to do in this section. All right. But everything in the homework before 44, you should be, well, I'm not gonna say you're gonna be okay with it. It's gonna be a learning process. But those problems are all doable. Okay. All right, well, I'm gonna end it now because I can't get into the next part without taking too much time. So I'm gonna end now. I'll hang out for a little bit if you have any questions.
Sir, what did you say in the first few minutes of class? I wasn't here when you were showing the graph of the grades.
Okay, yeah, I can go through that again. Let me stop my recording.